Folks, how are we doing today? So what we're going to talk about is Newton's second law of motion, which stems off of Newton's first law of motion, which we talked about in section 1, which states that an object at rest will stay at rest, an object in motion will stay in motion. Key thing within that is unless there is an unbalanced force. So we talked about how it really comes down to the whole idea of forces being balanced versus unbalanced. So as a little reminder, again, balanced forces means that all the forces are going to cancel each other out. The sum of all those forces would add up to 0, meaning that if I have some object with forces acting on it, if I have an up force, it'll be balanced out with an equal down force. If I have a right force, it'd be balanced out with an equal left force, such that the overall force would be 0 newtons. If one of those forces is larger than the other, they're going to be then unbalanced. So take, for example, if I have 1 newton up, 1 down, 10 right, 2 left, I can see here that obviously from right to left that those forces are not balanced. And when they're not balanced, they create then what's called a net force, which is the amount of that force that's going to be left over. So if I have 10 to the right and 2 to the left, that means there would be an overall net force of 8 newtons. So what Newton's second law is going to state is that when an object experiences that net force, it is then going to experience a change in its state of motion, whether it's going to speed up, slow down, or change direction. So Newton's second law states then that when an object experiences that net force, it is then going to accelerate. So understand, going back to last unit on motion, speeding up, slowing down, changing direction is going to represent an acceleration. Now that acceleration is dependent upon how much net force there is. Okay, so the more net force there is, the more push there's going to be in an object, the more it's going to accelerate. But Newton's second law also takes into account the mass of the object, which again is that inertial property of an object, how much resistance it has to any sort of push or pull. So it's basically Newton's second law kind of restates acceleration in a different way. It states that the acceleration an object experience is going to be a ratio of how much push or pull is acting on the object. And again, this is going to be the net push or pull, or the net force, to how much mass is acting on an object. So M stands for mass. So it's a ratio, again, of the push compared to the resistance. So take, for example, here if I have, a hand like pushing a block. So depending on the force that I apply to it, so if I apply a force to the right, okay, assuming that force is unbalanced, it's going to create some sort of motion, but we're also going to consider the mass of the object, and how massive it is going to dictate how much motion I'm going to give it. Okay, so the idea here then is that if I were to double my force, so if I were to push with twice as much force, obviously that twice as much force, considering the same mass, is going to create an acceleration that's going to be twice as big. Kind of the opposite of that then, if I were to then double the mass, so if I were to keep that same 2 hands on, double the force, but now again I double the mass to make that bigger, that's going to make my acceleration a little bit smaller. So it's simply a ratio of how much push you have in an object to how much mass or resistance that object has. Unit-wise, then, an acceleration can also be seen as a force per unit of mass. So it can be seen as a Newton per kilogram. And that's the other way in which we can define acceleration, is a Newton per kilogram that acts on an object. All right, so what we're going to do is we're going to look at the relationship between that net force, the mass of an object, and the acceleration experiences. So we're going to use Newton's second law, which states that it's simply the ratio of force to mass. All right, so if I give you a net force of 10 and a mass of 2, okay, so the amount of push versus the amount of resistance, if I divide those two out, 10 divided by 2 would give me 5. And again, units, we can think of this as newtons per kilogram, but if we remember back from first unit, that would be also 5 meters per second, okay? Now, if I were to double the force, so say I go up to 20 newtons now with the same mass of 2, I should see then my acceleration is going to go from 5 to 10. So notice here that when I double the force, that's going to cause my mass to double. So now let's see what happens when I double my mass. So if I double my mass, again, I still have my 20 newtons of force. I'm going to drop back down. 20 divided by 4 would still give me 5 meters per second. So again, the more force, the more acceleration, the more mass, the less acceleration is going to be harder to move. All right, now using this relationship again, we have acceleration as a ratio of force to mass. So understand you can see this equation different ways. Okay, you might remember way back from physical science, maybe seeing this, that the acceleration is the force over the mass. So if I think about this, I have A equals F over M, which relates the ratio of force and mass to find acceleration. But I can also use this relationship to analyze the force, which is simply the mass and the acceleration. I can also look at the mass, which is the ratio of the force to the acceleration. Okay, so here if I wanted to find the force, given that the mass is 2 and the acceleration is 5, what I would want to do here is multiply these two numbers to give me a force of 10. And then lastly, if I have the force of 10 and an acceleration of 10, if I wanted to find the mass, then I'm going to relate how much push to how much motion, so I know that this object would be a 1 kilogram mass by dividing those two. So again, different ways to analyze these variables, but it's just thinking about how much push, how much resistance, how much motion an object is receiving. Okay, so now let's take the idea of balanced versus unbalanced forces and Newton's second law. So again, Newton's second law, the whole ratio of force to mass. Understand that the force we're talking about here is the net force. Okay, so again, we're going to have to look at this in terms of diagrams. So if I see situation A here, where I have 3 newtons up, 3 down, 5 right, 5 left. If I think about the net force here, understand that the net force, whatever's left over here, would be 0 newtons because everything's going to balance out. So according to Newton's second law, if I take that 0 newtons, and let's say the mass is 1 kilogram, and I divide those out, I'm going to get an acceleration equal to 0 meters per second squared, or meters per second per second. So that again means that if there's no net force, if the forces are all balanced out, the object is not going to accelerate. Versus in example 2 or situation B, if I take that same idea here and notice that the unbalance of forces caused to the left, so I would have a net force, I'll just write as F, of 5 newtons to the left. If I take that and then divide it by the mass, which is 1 kilogram, understand then my acceleration, 5 divided by 1 would be 5 meters per second per second. Also understanding now this force is going to the left, so I can also think of this as a negative 5 newtons, which would create a negative acceleration. Now negative again is indicating direction, but depending on what this object is doing, especially seeing that this is friction, I can assume maybe this negative acceleration means the object is slowing down. So what sort of net force and acceleration we cause in situations C and D? So in C again, recognize that the net force based on 20 up and 20 down, I know the net force is 0, so this should cause an acceleration of 0 meters per second each second. Versus situation D again, now I have 15 newtons upward, okay, so I can think of it as a positive 15 newtons, divided by 1 kilogram, and I know that this object's going to experience an acceleration of 15 meters per second each second, and it'd be a positive acceleration that goes upward. Okay? So again, what we're doing now is what we're going to make the connection is look at whether forces are unbalanced or unbalanced, or balanced or unbalanced, find the net force, and then use that net force with the mass of the object to find the acceleration. So making the connection now between forces and motion. All right, so understand this is going back to what we kind of talked about at the very beginning of this chapter and understanding the idea of balanced versus unbalanced forces. So this is actually an example we saw in one of our earlier sections. So if we look at these two dot diagrams, what we have is an object moving to the right. So understand that the net force of the object is what's going to cause it to change its motion. So the car itself is what's going to represent the mass. So that car is going to have some mass to it. Okay, so if I see that an object is speeding up to the right, here's what I know. Based on the forces that are acting on it, say if I were to draw a little force diagram, if it's accelerating to the right, that means the normal force would be acting on it, gravity. There's going to be some sort of forward push, and then heck, maybe friction acting on it. But if I know this thing is accelerating or speeding up to the right, I know that there must be a net force acting to the right, which means that force to the right has to be a little bit bigger. Okay, versus the second diagram, notice the dots are getting closer together as time goes on. So this is the opposite case. If I were to draw a force diagram here, again, I would have my normal force and gravity. I might still have an applied force forward, but at the same time, friction is going to be acting against it or brakes or whatever it might be. But in this case, depending on what the forces are, if it's slowing down, that means it's going to be working against its motion. So the net force would be here. So the key thing is this, is that if the net force, this blue arrow, is acting in the same direction, that's going to cause it to speed up. If it's acting in the opposite direction, it's going to cause the object to slow down. Okay, so key thing here is that if we have same direction, that's going to represent speeds up. I'll just write with an arrow. And if we have opposite direction, that means the object is going to slow down. Okay, and that again is looking at the direction of motion and the direction of the net force. Okay, so let's do some quick examples, just some simple ones of Newton's second law. You have some tougher examples at the end. We'll save those for class. Let's say I want to find the acceleration of when I apply a 12 Newton force to a 3 kilogram object and then to a 6 kilogram object. So again, Newton's second law is going to analyze the ratio of the force to mass. So here I know it's 12 newtons of force, first acting on a 3 kilogram object, which would create 4 meters per second of acceleration. But if I compare that same force now acting to a 4 kilogram mass, so a little bit larger mass, I'm going to get 3 meters per second. So again, understanding that when you increase the mass of an object, that's going to decrease the acceleration. Next example, it says a net force, 15 newtons, is exerted on an encyclopedia, that's a book, to cause it to accelerate at a rate of 5 meters per second. Typo there, 5 meters per second squared, or 5 meters per second. So understand here that this is representing the acceleration, and then we have the 15 Newton force, so it wants to know what's the mass on that. So again, you can go back to the previous slide, but if I want to find the mass is going to be the ratio of how much force to how much motion it has. So force divided by acceleration. So I know that there's 15 newtons of force divided by 5 meters per second. So that means that object must have a mass of 3 kilograms. So what we're doing now is we're making the connection between the force experience, the motion, and then the resistance, which is called the mass. Last one here, it says, suppose the sled is accelerating at a rate of 2 meters per second. Squared again, that should be 2 meters per second. It says that the net force is tripled and the mass is doubled. What is the new acceleration of the sled? Okay, so if we know that it's accelerating at 2 meters per second squared, here's what we know. The acceleration is the ratio of force to mass. So if I were to, let's say, like it says here, triple the force, so I make that force 3 times bigger, and then I were to double the mass, what effect would that have? So understand that when you triple the force, it's going to take that acceleration of 2, and it's going to, when you triple the force, it's going to make it 3 times bigger. So if I multiply that by 3, that's going to give me 6. But by doubling the mass, that's going to cut that new acceleration in half. So that would result then in an overall acceleration of 3 meters per second. Okay, so we can work with these variables to understand that as you increase the amount of force or push or pull you're acting on an object, and obviously changing the mass, that both of those are going to have an impact on the motion of the object. And that's all that Newton's second law is about, is making that relationship, that connection between the force, the motion, and the mass, which is the resistance of the object. All right, we'll see you guys in class. Enjoy. Peace.